Here's an example of finding the arc length for a parameterized curve. We're going to have some fun here actually finding this arc length 3 different ways. Here's your arc length 3 different ways. And then we're going to compare the answers. Okay, the first way is to find the arc length on the curve between the 2 points shown. So that's this arc length along here. We're just using geometry. So you can see that 3 squared plus 4 squared on the triangle equals the hypotenuse squared, Pythagorean theorem. So when you solve that out, you'll get the length is 5. Now let's do it a different way. Find the equation of the curve and define the curve as a function. Then find the arc length using the arc length formula for a function. So it's a line, so we're going to take 2 points, 0, 3, 4, 0, find the slope. Then we use the mx plus b, or whatever method you want to do, and you get the equation of a line. So here's the function like that. Then you're going to get ready to use the arc length formula, so you have to do the f prime in there. So your formula is a to b, that's x equals a to b, whatever those are, a square root here. So that's the arc length formula. Put in our numbers. Our x's are going from 0 to 4. Our derivative of f is right here, there. Okay, plugging in, simplifying down. You're here. Now you're 1 plus 9/16 is 25/16. Square root is 5/4. That's 5/4. Factor out to the outside of the integral. 5/4. 0 to 4 of 1 dx. You work that out and you get 5. So it checks out. Now let's do it this way. We're going to parameterize the curve, then find the arc length of the portion between the 2 points shown, just as we did. So we're going to parameterize this entire curve, but then we're going to find that arc length there. Now of course we could just use the previous f of x we just found and write the parameterize sort of the cheap way, which is this, and have t's running from 0 to 4. And then we would use the arc length formula for parameterization, but it would end up looking exactly like the function form. So instead, we're going to do something a little different. We're going to start at 0, 3 at t0 and have the curve arrive at 4, 0 when t equals 1. And the way you're going to do that is going to take your 4, 0 destination point and subtract off the other vector 0, 3, and that's going to give you this red vector over here, so that you can add up 0, 3 to that red vector and arrive at 4, 0. Okay, so what you'll do is you'll get this vector difference that goes all the way from 0, 3 to 4, 0, shown in red. Okay, so that means on this picture that the subtraction did then equal 4 minus 0 gives you your 4, and 0 minus the 3 gives you negative 3. So that is the red vector. Okay, now back in point form, that means that the 0, 3 vector plus 4, negative 3 vector did arrive at 4, 0, and you can see that it does because 0 plus 4 is 4, and 3 minus 3 is 0. So it's checking out. So we want to cover all the points on the curve between 0, 3, and 4, 0. So we write the parameterization like this: 0, 3 plus a parameter times 4, negative 3. 4, negative 3 is a vector that's spanning the curve, covering the curve. This is your 4i minus 3j. That's the curve. By putting a parameter t in front of it and having that t go from 0 to 1, then you're covering all the fractions of that. So you're going to get this one and a little bit bigger, bigger until you get the whole thing. Okay, so now let's simplify that down. 0, 3 plus t, 4, negative 3. Put that t in on those two components. And then add to here, so it'd be 4t plus 0 here, and negative 3t plus 3, that's here. And simplify that down, all the while remembering that t goes from 0 to 1. Then we just write that out in a normal way for parameterization. The x of t function is 4t, the y of t function is 3 minus 3t, and the t parameter goes from 0 to 1. So let's check that out. When you're at 0, are you really at the point 0, 3? When you're at 0, this is 0, and when you're at 0 for the t, that's at 3, so that checks out. When you're at 1, by the time you arrive at the 1, are you really at the point 4, 0? When t is 1, 4 times 1, check. When t is 1, 3 times 1 is 3, 3 minus 3 is 0, check. Now we're going to find the arc length. So here is our function with, of course, t equaling 0 to 1. X prime is 4, y prime is negative 3. So the arc length is t going from 0 to 1 of the arc length formula for a parameterized curve, which is the speed here times dt, because speed times time, or delta t, is length. So we're adding that up, putting in the numbers 4 and 3. You square those out. 16 plus 9 is 25. Square root of 25 is 5. Factor out that from the integral. You're here. Evaluate the integral, and you'll get 1 minus 0. 5 times 1 minus 0, which is 5, and it all checks out.